I'm going to start recording now.
All right.
I figured out why this doesn't work. Do you think Amazon can send me a battery that's like small as a pencil eraser in time? Hey, I might get a. Nope.
What size battery?
Oh no, it's really small. It's really weird. So it's a cylinder battery, but it's like it's really honestly it's the size of the pencil with the green part. So not something we have. Oh no, it doesn't. All right, I'm working off two computers here today. The one that has the video and audio is a Chromebook, and then my desktop computer doesn't have a camera or speakers, but I can share the screen so you guys can see the work there. So I will be working over here. Then my second problem is I have my old version of a writing tablet, and the pen won't charge because the little battery in it won't charge. So we are stuck with me trying to write using the mouse. Now, fortunately, every single problem in both the homework and in the notes today, I've already worked them out. So the answers are there, but then unfortunately, you don't get to see me do the progression of this. So I will do my best, and you will do your best too. And then you're going to email me if you have any problems with anything that you see today or in your homework. And then when I'm back at school, which will be tomorrow, I can then do everything normal, and you know, we can take care of everything. So it's not that big a deal. Plus also, at least what we're doing here is related to what we've been doing the last couple classes. So therefore, you probably don't have as many questions anyway. Okay. I can't hear you at all. I guess I could probably hear you if you unmuted on the little Chrome. Just write something in the chat if there's something that you need me to explain in more detail. And I am going to turn my video off on the Chromebook because it's weird when I have to look at the side of my face and see all that gray hair on my beard. I'm not that old, but I am here. All right. So your homework assignment was Chapter 9, homework number 3, questions 12 through 15. We're going to just fly through this. I would like to be done by 10 o'clock or maybe a minute after 10 o'clock for sure. So, and there shouldn't really be anything that you need more than that. In question number 12, the importance, like we said last time when we were doing the notes or doing the homework assignment number 2, is you have two conservation of momentum equations where they stick together and where they don't stick together. And so if you see words like the collision is elastic, think about what you know that is elastic, like a super ball. If you bounce a super ball on the ground, we consider that to be an elastic material. Rubber is an elastic material. Now, it's not exactly the same meaning as what's being used here in the physics, but super balls don't stick to the floor like if you were to throw a wad of putty, might just hit the floor and splat. We would consider that to be inelastic. So that kind of logic should guide you as to which equation it is that you're going to use in each of these problems. Like I said, it's difficult for me to write here when I have to use a mouse to try to write the pen stuff. So I'm not going to. I'm just going to go to the answer slide and point out that because this was an elastic collision, the two carts don't stick together. So therefore, I have M1V1 final and M2V2 final separated from each other, and I start plugging in the values. All right. I didn't show all the math steps. I strongly suggest that you show all of the steps the whole way through so that I can find where your mistake is. Because if your mistake is minor, it might not cost any points. And if it does cost you anything, it too will also be minor. So you're going to be multiplying 0.7 times 2. That's going to be around 1.4. On the other side, you're going to be multiplying 0.5 times 2.5 is going to be 1.25. So this right here, 1.25. And we already said over here, this is 1.4-ish. Maybe 1.42 probably is what it is exactly without me getting my calculator out. I'm going to subtract the 1.25 to the other side. And when I do that, then I will have the 0.71V all by itself. So then I divide 0.7 to the other side, and that's how I got the answer 0.24. That's the best I can do for you right here. If you're having trouble with this algebra, a reminder, show your work. The more work I see, the more points I'm going to give. The final answer isn't that important to me as much as knowing that you knew the right equation. When the final answer becomes important is when the answer tells us whether or not the cart bounced backward or is still moving forward. So therefore, I do need the answer 0.24 for at least a point because I need to know that the cart, I guess I've got it labeled as cart 2, is still moving forward. So my numbers are backward of each other, aren't they? I called it M1V1 and then I named it cart 2 up above. That's just because I switched the order of the carts because I wanted to put the bigger cart in the front, but that doesn't really matter, does it? Okay, so that was question number 12. Question number 13, same idea. We're doing exactly the same thing. We're hitting a slightly smaller cart, and they're telling us that the cart moves away at 2.2 after the collision. So because I recognize this as a elastic collision, I write the equation where they don't stick together. I was going to see if I could. Can't move that little bar. Can I do this though? So we can't see the next step here yet. I'm going to have to erase it though. Will it? There it is. Okay. Let's cover up. Let's see what order I want to cover these up. Cover this and cover this. Okay. 0.505 traveling at 2.5. We put in 0.505 traveling 2.5. Collides with a cart that's at rest is 0. After the collision, the 0.505 cart, we don't know what its speed is, but the cart 2, the 0.610 cart, is moving at 2.2. And then we solve. I don't know what your numbers are going to be on your chapter test, but I will say this. There's not going to be any grams. Everything will be written in kilograms so that you don't have to move the decimal over at all. But I can't guarantee that you're not going to see decimals like these because these are the sizes of the carts that we use in labs. And so therefore, I want to maintain that consistency. If we get back to school and we are pushing carts across ramps on our lab stations, that you would recognize these are the consistent numbers that we see. Anyway, when you plug this all in your calculator, you'll notice that the calculator says negative 0.16. That negative sign is super important. It tells us that the car bounced backward. Okay? So that little tiny car, and it kind of makes sense. If a little car hits a bigger car, pushes the big car forward, that it would make sense that the little car is going to bounce backward. Question number 14. Ball 1 with a mass of 0.355 kilograms rolls frictionlessly across the table with a velocity of 0.095, collides with ball 2 that also has a speed. So this time we have them both moving in the same direction. After the collision, ball 1 continues in the same direction at 0.035. What is the speed of ball 2? Okay, so when you go to plug this in here, there's a whole lot going on there. Once again, let's cover these answers up and look at these one at a time. So here, 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 and here. Okay, so reading it in the order that you see it. Ball 1 with a mass of 0.355. is moving along at a speed of 0.095. You recognize by the context of this problem that they didn't stick to each other. And so therefore, I use that equation. Then once I've chosen that equation, sorry, I'm kind of tripping out. You guys have already noticed these things before, but for me, this is the first time seeing the cursor moving on the screen when I am one of the participants in class and seeing that sometimes it looks like it's a seal. And then a moment ago, it looked like the shapes, but interesting though, the shapes that Zoom reads to be what the cursor is doing. Anyway, there's your first ball. Second ball is moving along in the same direction, so that one is also a positive number. It makes sense that if the second ball is traveling slower, the first ball is going to collide with the second ball. After the collision, they tell us that the first ball is moving now with a speed of 0.035, and we want to know what is the second ball doing. Show your work, because the difficult part about this is the math. Right? You got to plug all these numbers in. I would actually do the multiplication here, get an answer, do the multiplication here, get an answer, do the multiplication here, get an answer. I would write all those things down on my test. Then I would start adding these two together on this side, subtract this one to the other side, then divide by the 0.710. One of you just sent me an email where you were like, I don't understand what just happened here on a problem like this. And my response back to you was just one of those responses that email lets me put. But to say it to you in Zoom, I don't really care. If I see all of this stuff written down correctly here, you're already looking at like 4 out of 6 points. Then maybe if you do a little bit of the math work, now you're up to 5 out of 6 points. So with the curve, you're still looking at 100%. So it's not a big deal. Question number 15. Same thing now. We have a 0.5 kilogram ball traveling at 6, collides with a 1 kilogram ball moving in the opposite direction. These are the kinds of things that I am looking for on your test, is that I see that you have a negative sign. Let's point an arrow at that negative sign. That this says that it's moving in the opposite direction. Remember that velocity is a vector, and so therefore the direction matters. After the collision, the 0.5 kilogram ball bounces backward. That tells me that this has to be a negative. By the way, I'll be writing so many versions of the test that if we could actually do a kinetic energy calculation on these problems, we might find that these problems are not possible. Don't let that bother you. Most of you don't know that formula yet anyway, because we haven't learned energy. But it's very possible this is not even a realistic situation, but the math will still work out. So solve for V2F. The signs matter. You'll notice that V2F comes out to be 2 meters per second, also negative, which means that it's still rolling in the same direction. So in the final answer, we can say that this one also is moving this way. Okay? And I want to repeat, show your work, because the majority of the points are where you show me that you get the physics of it, not that you can do the calculations. This is not an engineering class. This is a physics class. Okay? Show your work. That was your homework assignment. That brings us to today's notes. It is called explosions, but no, it's not that exciting. Explosions in physics are solved using conservation of momentum. A true firecracker explosion, if you blew up a firecracker and you could look at it like with one of those cameras that they use in Mythbusters, you would still see conservation of momentum. So it still fits this bill. It's just that we're not looking at something so fast like a chemical reaction. But something like the recoil on a gun is a perfect example of an explosion in physics. We're going to look at momentum needing to be conserved. Now, normally what I would do at this time is I would draw a picture of a gun, and I would put a little bullet inside of the barrel, and I will try to do that while you're still copying this down. But just remember that if it looks lame, I can't help it. Not bad, actually. Like a handgun, maybe? Yeah, it even says handgun. Put a little bullet inside of there. Okay? Before the collision, there is no momentum. So when we write down our momentum equation, we're going to say M1 V1I plus M2 V2I getting there, equals then what happens after the two things explode apart. So originally, there is no momentum to the gun. There is no momentum to the bullet. After the explosion, though, now notice that it does say grams. I will do a problem like this one on your test that involves kilograms and kilograms so that we don't have to do any switching of units. I don't want that to be the reason why your answer comes out to be something absurd. So after the collision, of course, we would say M1V1F plus M2V2F. And then in that, we were solving for the recoil of the gun. So its mass of 1.276 times V2F. And then the bullet, 10 grams, is and we'll just leave the zero out, 0.01 kilograms. I wouldn't even put the units in if I was you solving this, because why let them get in your way while you're trying to do the algebra? And then times the final speed of 366. So really what this comes down to is the easiest of our conservation of momentum equations, because all we're doing is solving for V2 right there to make this work. I am going to go to the next slide where we can see the answers for this. That looks a lot prettier, doesn't it? Solving for V, what I would do is take 366 times 0.01, subtract it to the other side. When you do that, you are going to get a negative. So please understand that when you solve this out, I'm going to put a little negative sign here because I know there's people who go back and do these notes, watch these videos, and if you do that and you get an answer of 2.9 with a negative sign, you're like, how come he doesn't have the negative sign? It's because I'm analyzing the picture, and in the picture, I see the bullet traveling to the right, and then the gun recoils to the left, but I can't draw the picture on there because I don't have a nice writing tablet right now. Then it also asks us what is the momentum of the gun after firing. So then I just take the 1.276 and multiply it by that 2.9. And technically, what I should say with this momentum is that it's in this direction. Okay, so on your test, if I do or don't see that negative sign in an explosion problem, I don't mark it wrong. But in the test on the previous section, the sign matters. So therefore, my suggestion to you, always put the sign. If your calculator gives you the sign, put the sign. I think I have one more example, then we're all done. An astronaut floating in space wants to get back to the space station. He's trying to get back to the space station restaurant. Apparently it has great food, but no atmosphere. Nobody?
Yeah.
He has a jetpack on, fires the thrusters, and 35 grams of hot gases are expelled at 875 meters per second. If the astronaut has a mass of 84 kilograms, how fast does the astronaut move, and in what direction should he direct the exhaust gases? While you're copying that down, you don't need to copy down the red, of course. That was just a not so funny joke. While you're copying down this example, I want to tell you about a good movie, maybe to watch, maybe not to watch. It was called Event Horizon from back in the early 2000s. And it was actually a horror flick that takes place in science fiction in space. And what it is I think it was Lawrence Fishburne was the captain of this salvage spaceship, and they go and salvage a spaceship that had went through a black hole and come back out. And so they go there, and of course the scary part of it is the fact that it has brought some kind of evil entity along with it back from great, now I'm gonna get a bunch of pop-up messages. It brought back some kind of evil entity from the black hole. So that's why it's a scary science fiction movie. But one of the things that's neat about it is at one point in time, one of the astronauts, while they're working on the outside of this ship that they're trying to salvage, gets knocked away from the spaceship. And, you're floating through space. How do you get back to where you came from? I imagine we could probably even say the same thing could have occurred in that movie Gravity. I just don't remember it. Couldn't you use, if you have some kind of, I'd hate to say that you would detach your breathing apparatus, because now are you going to allow this pressurized spacesuit to start releasing gases out into space, you're going to die. But if it was possible to have something that just released a gas, you basically turn yourself into a mini rocket. Now, I can't draw a picture for this like I would do if this was a normal class, so you maybe have to supply your own picture. But can you understand that as the gases go one direction, the astronaut is moving the opposite direction? Before the gases are released, there's no momentum. But after the gases are released, there is momentum for each of them in the opposite directions. Because no, I don't need it too. That's okay. I don't need it. Thank you though. Because the gases have such small mass and such high speed, that then kind of counterbalances the fact that a larger mass of a person with their spacesuit would then have a very small velocity. So when you're doing your tests, don't be afraid to look at your answers and go, does that seem legitimate? Because as much as possible, I will make your answers seem legitimate. It's just that some of them aren't physically possible because of kinetic energy, which we haven't learned yet. But they will all seem legitimate. So you can analyze your answers. All right. Your homework assignment is Chapter 9, homework number 4. Can somebody say amen in the chat so that I know that you guys are out there listening right now? And then I'm going to say to you, you can go. Thank you. You're good people. Look at all of that. Excellent. You're all there. If you have any questions on this, all jokes aside, email me. I'll help you out. I'll send you any pictures, whatever it is that you need. Chapter 9, homework number 4. You guys have a great rest of your day. I'm going to shut this off now. Hold on.
I'm gonna